Good morning, everyone. First, I'd like to thank you, Professor Shah, for inviting me to this talk. My name is Eunji Pak, and I'm working at ETRI. ETRI is a research institute of Korean government that is specialized for electronics and telecommunication. Today, I'd like to share our experience of implementation of shared resource partitioning mechanisms on a commercial RTOS. Here's the agenda of this talk. I will first introduce Q+Air, a commercial RTOS that our team has been working on. And next, I will introduce the recent work that implementation of shared resource partitioning mechanisms on Q+Air. Q+Air is a RTOS that ETRI has been developing. At first, the first release of Q+Air has been developed from 2010 to 2012 as a main operating system of a integrated flight control computer of unmanned avionics vehicle. At that time, our client Kai wants to integrate mission control, flight control, commands, and communications in one system. So we decide to implement the ETRI 653 and its concept of partitioning. ETRI 653 defines the robust partitioning, which is composed of special partitioning and temporal partitioning. Special partitioning means that an application cannot access the memory space of other applications, and temporal partitioning means that an application cannot affect the timing activities of other applications. So as shown in the figure, there's two partitions, P1 and P2. They do not share the memory space and they do not share the time window. With the support of partitioning, we can integrate multiple applications with different degrees of criticality, as I told that mission control, flight control, and commands and communications in one system. The another requirement of our client was a certification. So the first version of Q+Air is a certifiable package for DO-178 level B, the highest design assurance level of avionics safety. And different from other ETRI 653 compliant RTOS, which that implement partitioning using the hypervisor technology, we implement partitioning in a kernel level to make our RTOS lightweight. Recently, from the 2014, we are extending the Q+Air to support multi-core platforms. Actually, 2014 is the year that I started working at ETRI, so actually I'm not the original developer of Q+Air, but I'm in charge of supporting multi-core platforms. Interestingly, Q+Air has its commercial version named RTOS. The commercial version is managed by ETRI's spin-off company. After the first version of Q+Air has released, the early developed members established the company named Artist. In the name of Artist, RT means that real time and art. They told me that developing an OS is like an art. Artists focus on the automotive and avionics markets, so they are extending the RTOS to support the AutoSAR, and they are preparing for the ISO 26262 certification. After the artist established, we are cooperating with each other. Mainly, ETRI focus on the research issues, and artists focus on the commercialization. Since the first release, Q+Air has been deployed to various safety-critical industrial applications like unmanned avionics vehicle, tilt rotor, nuclear power plant, helicopter, subway screen door in Brazil, and self-propelled guns. And now we are participating in the project of autonomous driving car. Now I will present the comprehensive shared resource partitioning implementation on Q+Air. Here's the agenda. As mentioned earlier, Q+Air supports robust partitioning of ETRI 653. However, the robust partitioning support is no longer be valid in multi-core platforms. As you know, in multi-core platforms, cores share the hardware resource such as cache, memory, or I/O device, and multiple applications try to access those resources at the same time. The time waiting for access grant directly affects the execution time of application. This inter-core interference problem, or shared resource contention problem, is a major source of timing variability. As a result, in most safety-critical systems, we had to turn off but one core. So RTOS must deal with the resource contention properly so that diversity of tasks stays guaranteed and tightly bounded. And especially it's important for safety-critical applications like avionics that require certification. Recently, FAA, Federal Avionics Administration, published the position paper, and the position paper discussed the need of inter-core interference mitigation. So to support robust partitioning even in the multi-core platforms, we integrated a number of resource partitioning schemes, each of which targets different shared resource on Q+ware. Today, I will present our experience and of implementation, focusing on the issues and challenges that we experienced. I will start with introducing the P4080 hardware platform that we have chosen. As shown in the figure, it has 8 cores, and level 1 and level 2 caches are private to each core. However, level 3 caches, memory controllers, memory modules, I/O devices, and these 8 cores are shared through the memory bus called coordinate fabric. So these are the shared resources can be a source of inter-core interference. In this work, we focus on the L3 cache, memory modules, and this coherence interconnect fabric. This is the reason that we have chosen the P4080 platform. Recent PowerPC platforms, including the P4080, support hardware feature called robust partitioning. With this hardware support, we can configure the system as this figure. There are 4 partitions, which is marked different colors, and each partition has its dedicated hardware resource. First, each core is dedicated to each partition, and we can divide memory, main memory, physical memory, into several physical regions, and we can assign each region to each partition. And also, the L3 cache can be partitioned to multiple regions and assigned into disjoint cache spaces and allocated to each partition. Likewise, I/O devices can be partitioned to allocated to each partition. Actually, it's interesting to me that the P4080 platform also provide the way to restrict the coherence overt, cache coherence overt. We can disable the cache coherence for some partitions, or we can specify a group that really participate the cache coherency. Okay. I'm sorry.
Let me switch back to this. Try.
Yeah, thank you. As resource partitioning mechanisms, we implemented 4 techniques. We implement partitioning mechanism for the memory bus and memory bank and shared cache. For the shared cache partitioning, we implemented 2 alternatives. One is set-based partitioning and one is way-based partitioning. After we implemented these 4 techniques, we combined all these techniques and integrated on Q+Air. During implementation, we encountered a unique challenge that related to the paging. So actually, we don't have a paging scheme in our operating system, but we had to add the paging scheme to implement these partitioning techniques. First, to isolate the memory bus, we implemented the memory bus bandwidth regulator. I attached the reference in the bottom. This figure illustrates how the memory bus bandwidth regulator works. We first set the memory bus bandwidth budget for each core, and system monitors how many requests come from each core to memory bus. And if a particular core exhausts its budget, system generates an interrupt. So if interrupt is generated, operating system throttles the further execution of tasks on core 1 to prevent core 1 using the memory bus. So from step 1 to step 3, we implemented by configuring the hardware registers, performance monitoring registers or performance monitoring counters. And for step 4, we modify the operating system scheduler. During implementation, we had to set the period of these 4 steps carefully. If the period is too short, overhead becomes excessive due to the frequent interrupt occurs. But in contrast, if the period too long, we cannot keep the predictability. So we set our default period of our implementation as 5 milliseconds. But because if we use the shorter period, the frequent interrupt affects the performance. But in the original paper, the period of this memory bandwidth regulator was 1 millisecond, so I think that we have a room to improve our implementation. Next, to isolate the memory bank per each core, we implemented DRAM bank aware memory allocation. This illustrates how it works. An application requests memory to run the program to the operating system. Then operating system allocates a portion of physical memory to an application. At this time, this virtual memory is a kind of view that kind of a memory of applications view. So at this time, operating system stores the virtual memory to physical memory mapping in the page table. At this time, if we look the address of physical memory, we can know where this data goes to which bank in the memory module. So we changed the memory allocator of Q+Air to check these bits and allocate memory in such a way that each core uses separate memory banks. As a cache-based partitioning, we implemented 2 alternatives, set-based partitioning and way-based partitioning. To provide set-based partitioning, we implemented page coloring, the same implementation as used in the memory bank partitioning. I will briefly explain the page color. Here's the memory address, and among this memory address, bits from 715 in our platform represents the location of L3 cache. It is the index for the L3 cache sets. Among these bits, there is a intersecting bits with physical page number. Physical page number is operating system can control the physical page number. It means that if we change the physical page number, we can control the hardware cache location of hardware cache. So we call these intersecting bits as page color. So as shown in this figure, data belonging to this yellow color can be only cached to the cache sets of the same color. So when an application requests a memory, operating system allocates physical memory considering this color. As a result, the L3 cache is partitioned to each application. During the implementation, we encountered the L2 co-partitioning problem. There is as I told before, mentioned before, this is a P4080 memory address mapping, and bits from 7 to 15 indicates the location of L3 cache. And among these bits, some intersecting bits that indicates the location of L2 cache. So if we use these intersecting bits to partition the L3 cache, it has a side effect of partition the L2 cache. But the L2 cache is private to each core, so we do not have to partition the L2 cache. So we added a rule during implementation that only the 14 to 15 2 bits allowed for L3 cache set partitioning. It means that the number of cache partitions is limited for. So if we use the set partitioning mechanism to 8 cores, it means that some cache sets will end up shared by 2 cores. Now I will present the implementation of way-based cache partitioning. The way-based cache partitioning is implemented using the feature supported by the P48 hardware platform. First, we divide the physical memory into disjoint cache memory partitions like this, and we configure the local access window register and memory management unit of P48 hardware to set up the physical memory like this. Then we configure the L3 cache related registers to partition the L3 cache in a way granularity. This L3 cache has a 32 ways, and we can partition the L3 cache up to 32 parts. It's different from the set-based cache partitioning. So with the way-based partitioning, we can relax the restrictions of the number of cache partitions, but the way-based cache partitioning cannot be integrated with the set-based cache partitioning or memory bank partitioning because they use the page coloring. Here's the reason. If we want to implement the way-based partitioning, we have to allocate a memory in this way, in a sequential way. However, if we want to use the page coloring, we have to allocate memory in an interleaved way. So because of this conflicting requirement of memory allocation of this mechanism, so we cannot combine the way-based cache partitioning to set-based cache partitioning or memory bank partitioning. If you use the other architecture like which supports cache way locking, you can combine this, but this may be relevant to all other PowerPC models. Now I will present the unique challenge related to paging. Page coloring, which is used in the set-based cache partitioning in memory bank partitioning, assumes that operating system manages the page with fixed sized pages. However, it's not true. Actually it's true in general purpose operating system, including Linux. However, in most RTOS for safety critical systems, we do not use the paging scheme because it causes the unpredictability of timing. So Q+Air does not use the paging. Here's the original memory management of Q+Air. We manage the main memory as in this figure. We manage the main memory with variable sized pages. Region for the kernel code, kernel data, and partition is managed by one big page. It's different sizes. It means that we need only one translation information, TLB entry for each region. And even Q+Air locks that entry in the TLB. So first are the mapping data to stay in the TLB, and it ensures the performance stays within a predictable range. In P48 platform, we exploit the memory management unit of hardware. In P48 platform, there is 2 levels of MMU, memory management unit. level 1 is managed by hardware, but level 2 is managed by software. So we use this level 2 MMU. And it has two kinds of TLBs, one for variable sized pages and one for fixed size pages. So we use the TLB for variable sized pages and use the TLB locking mechanism of P48 supports. However, in this work, this was the original memory management in Q+Air. We modified the memory management of Q+Air to implement the page coloring, resource partitioning mechanisms. So we changed that memory management to manage applications memory regions with 4 kilobyte pages. We did not change the kernel management of kernel regions to find the performance predictability of kernel execution. So I will present time overhead of paging. I hope you note that this is the simplest implementation of paging. I mean that it is not optimized yet. To measure the paging overhead, we run the synthetic benchmark with changing data size and access pattern. And we measure the average memory access latency. In the first figure, the access is in the we access the data in a sequential way, so the TLB miss rate is not that high. In that case, time overhead due to the paging was 6%. It's not that big. But in the second graph, as you can see, with the same benchmark but different access pattern, the performance degrades up to 197%. In this experiment, access pattern is fully randomized, thus the TLB miss rate is much higher. First, I thought that our implementation was long, so I have checked our source code. However, after counting the number of TLB miss, I found that the performance degradation is due to the architecture of P48. Here's the scenario. There is a 2 levels of TLB in P48 core, and L1 TLB has a instruction and data TLB, and L2 TLB is a unified TLB. So, this green box is a TLB entry for code, and blue box is TLB entry for data. As you can see, the TLB entry for code is small to fit in the L1 TLB, instruction TLB. But as the data size increases, L2 TLB is mostly filled with the TLB entry for data, and the TLB entry for code is evicted. And as a result, to keep the inclusion property, as L1 TLB and L2 TLB is L1 TLB is an inclusive cache of L2 TLB. This TLB entry for code also evicted from the L1 TLB. So L1 instruction TLB miss occurs even if the code size is within the L1 instruction TLB coverage. So the performance degradation was too high. But interestingly, in next generation PowerPish core, we found that this L1 and L2 MMU is no more than not inclusive. So actually, we conclude that we need the predictable paging if we want to use the resource partitioning mechanisms in an RTOS. So there are some studies focused on the predictable paging, or there are codes hardware provides means for implementing predictable paging. But for now, we focus on the resource partitioning mechanisms, and we let the predictable paging as a future work. So as I explained, we implemented 4 techniques and paging. I will denote each mechanism as a RP bus, RP bank, RP cache set, and RP cache array. Then after we implemented 4 techniques, we combined these techniques. But as I told before, we cannot combine the way-based cache partitioning with set-based cache partitioning or memory bank partitioning. So there is two possible integration options. First, we can combine memory bus partitioning, memory bank partitioning, and set-based cache partitioning, because these two mechanisms use the page coloring. But in this case, due to the restrictions of the set-based cache partitioning, restrictions of the number of available cache partitions exist. Here's the second integration option. We can integrate memory bus partitioning and cache wave partitioning. But in this case, contentions on memory bank is unavoidable. Here's the evaluation. Our hardware platform is P4DAD and software platform is Q+Air. We use the synthetic benchmark latency and bandwidth. And as a performance metric, we measure the average memory access latency and normalize it to the best case performance without interference. And we made two benchmark mix that can show the results well. We first made the full core mix. We configured this mix to cause contention on all the memory resources to evaluate each partitioning mechanism and integrated mechanism. And we also made the full core mix, 8-core mix, to show the limitation of set-based cache partitioning. Here's the evaluation results. This graph depicts the performance when RP bank, RP cache set, and RP bus are integrated to the RTOS one by one. The worst performance means that the performance when the performance is most degraded due to the intercore interference. And the best performance means that the performance when there is no interference. We executed an application alone. From the worst case, as we apply the partitioning of memory bank, we see that performance improved about 10%. It is because the RD cores are enabled to access memory banks in parallel. And now we add the set-based cache partitioning, and we found that the performance of application running on core 1 increased a lot, 56% improvement compared to the worst case. It's because that the application running on core 1, its data size is small to fit in the last level L3 cache. But due to the contentions, so if there is no contention, the access to the data will end up L3 cache heap. But due to the contentions, data over application on core 1, it exhausts, so it degrades the performance a lot, but we can improve the performance with the cache partitioning. At last, we add the bus-based memory bus partitioning and performance. This is the performance when all techniques are put together. Here's the result of the integration option 2. We combine the way-based cache partitioning and memory bus partitioning at this time. At this time, memory bank partitioning is inapplicable, so we cannot avoid the memory bank partitioning. Here's the worst case performance, and here's the performance that we apply the way-based cache partitioning, and here's the performance that we add the memory bus partitioning to way-based cache partitioning. In this benchmark, however, the memory access is not concentrated to a specific memory bank, so the performance is sufficiently comparative. However, worst case could arise depending on the task behavior, and in that case, we cannot handle the memory bank intercore interference on memory bank at that case. And you can see the paging overhead compared to this graph and this graph. This one is apply the way-based cache partitioning. Performance applied the way-based cache partitioning. And this is the performance when we use the set-based cache partitioning. The difference is the paging. So if you compare this graph and this graph, you can see there is a difference between performance. There is a paging 3%, 16%, 70%, and 13% performance degradation due to the paging. So you can see the paging of by comparing these two graphs. This is the last experiment results. In these results, we can see the limitation of set-based cache partitioning by comparing the graph B and graph D. As you can see, compared to the worst case, if we adapt the set-based cache partitioning, the performance increases. However, if we use the way-based cache partitioning instead of set-based cache partitioning, performance improvement was about 24% more. So, as I mentioned before, if we use the set-based cache partitioning, some cores should share the cache space. So, this is the performance due to the limitations. So, and you can see the overhead of paging by comparing this graph and this graph. With today's talk, I've shared our experience of implementing multiple shared resource partitioning mechanisms on our operating system. And as a future work, we will plan to implement predictable paging, and we want to evaluate our implementation with real-world applications. Thank you for the attention, and if you have interested in our work or Q+Air, or if you want to buy the RTOS, please contact me with this email address. Thank you.
Thank you very much, Eunji. And now, any questions? Yes?
Yes, as to buying the RTOS, is that open source or it's just by the binary code?
You mean RTOS?
RTOS, the software you have.
It's not the open source yet, but we are planning to make an Q+Air as an open source.
Okay, so I have a question. When you are talking about you are trying to certify the OS, and what's the most difficult part in this process?
Actually, I've mentioned before, I'm not the original developer, so I didn't do the certification thing. But my colleagues told that there is lots of paperwork. And
Okay, so all of these techniques you talk about, right? Did you consider the blocking due to the kernel space? For example,
I see.
Like when you are doing the scheduling or something like that, it's blocking the kernel space, and then the core cannot do anything.
Actually, we considered that, but for now we didn't. But I'm planning to do that because. In some paper, they told that the kernel's contention on the kernel space is not that big, but in some paper, they told that, we need to separate the kernel space, so I will try to.
I see, but it still goes through the certification part, right?
Oh, yeah.
Okay, thanks.
So I do congratulate you on this work. This does some things that most commercial operating systems won't do. That is using the actual hardware in the Core IQ processing architecture for the hypervisor. Normally that's done up in a software layer so that it can be used across multiple processor technologies. But the P4080 is not the newest thing.
Yeah, I know.
In that architecture stream, and PowerPC is starting to be questionable of what its future is. It's the T series is the latest, and then LS series, which has some commonality in structure, especially the fact that it's is using what's the right word? Cluster computing architecture. That complicates some of the things that you're doing here, and I'm wondering whether or not there is any work at looking at using some of these techniques and augmenting them for the cluster computing environment.
Actually, we are working on the T2080 these days. And as I understand, the T2080 supports the robust partitioning feature. So I think that it is not that tough. We use these mechanisms in the next generation PowerPC processor. Yeah, as I think.
I think this is might be the last question.
Just very briefly, it was not clear to me what application you use for the benchmarks.
Oh.
The experiments.
Actually,
Did you mention that or I missed that?
yeah, actually we use the synthetic benchmark. It's not the real world benchmark. It's the synthetic benchmark which is used in many research works, papers. Yeah, but we couldn't adapt the real world applications we are planning to.
Okay.
Thank you.